Hello everyone, I'm Frank, and welcome to Frank Puzzles, and this is today's hard level difficulty puzzle, and it's called Magic Matryoshka by Nahilion. And here are the rules. We have irregular Sudoku rules applied, which means in every cell in the grid, place a single digit from 1 through 9, such that there are no repeats in any row, column, or designated 9-cell region, which can be various shapes. Excuse me. So this is a designated 9-cell region. You cannot have repeats in that region. Same with this region, etc., etc. So that's irregular Sudoku rules. We also have digits separated by a black dot have a ratio of 2 to 1. So these are black Kropki dots. So for example, if this were, say, a 4, this would have to be a 2 or an 8 to maintain the 1 to 2 ratio between them. And that's an example of how black Kropki dots work. And then, finally, we have the Magic Matryoshka part of this puzzle, which is the entire 9x9 grid is a magic square, which means that the rows, columns, and diagonals of that 9x9 square must add up to the same sum. And that's what it means to be a magic square for a 9x9 grid. To be a magic square for a 7x7 grid, we need those 7 digits must equal the same as the 7 digits along the diagonal. So every cell, every row in the 7x7 grid must add up to the same sum, and it must equal the same sum as every column does, and that must equal the same sum as the diagonals do in the 7x7 grid. So this is the Matryoshka part of the Magic Matryoshka, and that they are essentially magic squares, which is why it's a Magic Matryoshka. So and that's in the center of the 9x9 magic square is a 7x7 magic square, right? Where basically every row sums up to the same sum, which is equal to the same sum as every column, and both diagonals, both seven cell diagonals. So and in the center of that 7x7's magic square is a 5x5 magic square here, which again, every row must add up to the same sum, which is equal to the same sum as every column, which is also equal to the same sum as the digits on the 5-length diagonals in this 5x5 box. And then in the very center is a 3x3 magic square, which again, the rows have to add up to the same sum, which is equal to the same sum as all 3 columns, which is also equal to the same sum as the diagonals. The 3-cell diagonals in that 3x3 square. Pretty interesting rule set here. I do like the embeddedness, so that's why I chose to try to solve this, because it's an interesting idea, and I don't really have the I've never done anything like this, so I don't really know how this is going to turn out, but I sort of have some intuitions here, but we'll get to that when I start solving it. Anyways, those are all the rules. If you like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's go. Okay. For a 3x3 magic square, actually, you know what? I'm going to pause because I need to go to the bathroom pretty badly right now. We'll get to the solve right after I get back. Okay, so I'll be right back. And I'm back. Apologies for that. I should have probably actually went to the bathroom before I said let's go. But let's go now. Okay. On a 3x3 magic square, I know that to add up to those sums, it must be 15, right? And we know 5 is in the middle. because to be part of 1, 2, how many? So it's 1, 2, 3, 4 different sets that add up to the magic number, which is 15. Because since every row and every column adds up to the same sum, those sums must be equal, right? So you have 3 times the same sum equals the total sum of the digits 1 through 9, which is 45. 45 divided by 3 is 15. So every row and every column and every diagonal in a 3 by 3 must add up to 15. So we are guaranteed that this is 15 here. So the only digit that can be part of 4 unique sets, well, it's not, well, the only digit which can sum up with the other 8 digits to add up to 15 4 times is 5, right? 5 can be with 1, 9, 2, 8, 3, 7, and 4, 6. And it has to be with each of those sets separately, right? So that's why we know this middle digit is 5 in a magic number, in a 3 by 3 magic number. Well, these corners have to add up with these 2 digits. So this corner has to add up with these 2 digits to add up to 15. Same with these, and it has to add up with the 5 to add up to 15. What possible combinations are there? The only ones can be essentially even digits. If you have an odd digit plus this is odd, the problem is one. Okay, so the issue is basically 1 and 9, right? 1 and 9 can only add up to 15 with 5, 9, and 6, 8. 9 similarly can only add up to 15 with 1, 5, and 2, 4. So 1 and 9 are guaranteed to not be in the corners. Because 1 and 9 are not guaranteed, they have to be essentially in the row or the same column. We're not sure which. Because of that, one of these sets are odd. You can't have another odd adding with it to add up with an even digit to add up to 15, right? Because 15 is an odd number. To add up to an odd number, you need, for 3 digits, you need 1 odd and 2 evens, or 3 odds. Well, you can never have 3 odds because we have a 5 here, and to add up to 1 or 9 here, if you have a 1 or 9 in, say, the columns here, that means 1 has to be here, or 9 has to be here, or 9 has to be here, and 1 has to be here. You cannot ever have 2 odd digits with it to add up to 15, because the only odd digits left in that box are 3 and 7. 3 and 7 and 1 adds up to 11. 3, 7, and 9 adds up to 19. So that's never going to work. Therefore, they must be with 2 evens to add up to 15. So that's why you know these corner cells all have to be even. So these are 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And this must be 1, 3, 7, 9. Okay, so that's this is basic knowledge that I had previously of 3 by 3 magic squares. Obviously, 9 by 9 magic squares, they're all going to add up to 45. Now, the question is, how do 5 by 5 and 7 by 7 magic squares work? That is going to be the question. We know along the diagonals, they eventually must add up to 30. But we don't know if there's a specific order that they have to go in. Right? Does it have to be... Well, we don't even know. Yeah. Is there anything that we have for that? I don't know if we have any additional information there. I don't think there's a guarantee for the magic squares of 5 by 5 and 7 by 7 to have any particular sum. It doesn't have to be 20 though. That's the thing, right? So if you normally expand each region by surrounding it, it would have to be 5 by 5. The 5 by 5 is not guaranteed to expand by 5, right? But on average, is going to have to expand from the 3 by 3, it's 15 for every row and column. If you expand it to 5 by 5, it could add 5. Was it 5? No, it's 15 to 45. It has to be 10. So it would be 25, right? But it's adding 10 for every set, right? So that's on average what it's going to do. But it's not guaranteed to be 10 for every set, right? So from the 3 by 3, that's 15 for every row, column, and diagonal. For 5 by 5 on average, it has to be 25, but it doesn't have to guarantee, right? Because then 25 for the 5 by 5, 35 for the 7 by 7, and 45 for the 9 by 9. But it could be something like 26 for the 5 by 5, then 34 for the 7 by 7, and then 45 again for the 9 by 9 for every row, diagonal, and column. I think Fistemaffel's ring theory does work, but is that helpful? I don't even know. We do know. What do we know? I'm not really sure. So Fistemaffel's ring theory, I think, still satisfies. Because we know this 3 by 3 area is guaranteed to be the digits 1 through 9. Because it's a magic square. And Fistemaffel's ring theory is basically that you have these digits, which are guaranteed to be 5 sets of the digits 1 through 9, because they're 5 rows. And that's the same as these sets. This is 4 sets of the digits 1 through 9. Actually, what is it? You wanted these. Right. So these are still going to be this 4 sets of the digits 1 through 9. You subtract out this, that's going to be 4 sets for the green region and 4 sets for the blue region. And then you subtract out the cells that they share in common. And voila, it's still Fistemaffel's ring theory is still satisfied. But does that tell us anything? I don't think it really does, right? Because while we do know that the 4 corners is equal to the green, and obviously this is a 5 by 5 magic square, we don't have much information about what that entails. So, I don't know if that, like, gives us anything, right? What does that mean? I don't know. Okay, we do know something, though. These 2 digits must equal the same sum as these 2 digits, which must equal the same sum as these 2 digits, which equals the same sum as these 2 digits. So we are guaranteed that. The question, though, is what is that sum, right? And that's why I was like, on average, it has to be 10 if you expand to the 5 by 5, if you expand to the 7 by 7, again 10, and again 10 from the 7 by 7 to the 9 by 9. But we are not guaranteed that, though. That's the thing. On average, it's going to have to have an expansion of 10. And it's just going to have to be varied within there, right? So again, it could be like 11, 8, 9, or whatever, of some combination to add up to 30. But we don't know what that is. But the thing is, so the sum of these 5 and the sum of these 5 must be the same. Same with the sum of these 5 and these 5. Does that tell us anything? I'm not sure. Well, one thing we do know is because of the irregular regions, where is the 5? The 5 in this irregular region cannot be here, so it must be in this Vistimefeld ring. Does that tell us anything? Again, I'm not sure. In this 5, we don't have a 5 here in this region because there's already 5 in that region. Where is the 5 then? The 5 cannot be next to a black Kropke dot because that's 1, 2, 3, 4, 6, 8 as possibilities. So 5 in column 9 must be one of those two cells. Does that tell us anything? Again, I'm not sure if it does. These 4 digits must match these 4. Again, does that tell us anything? I don't know. Anyways, let's get rid of Vistimefeld's ring. We know that it works, but we don't know if that's helpful. So these 2 digits must be here, and it can't be the 5. So they have to be some combination here. If this is 7, 9, that's interesting. Then this is a 5, 7, 9 pair, and then these 2 digits must be the pair that are here. But does that tell us anything? I don't know. Again. We do know, again, so for every iteration of these magic squares, we always know the corner 2 digits must equal the same as these corner 2 digits summed up. Same as these 2 digits summed up here. Actually, same as these 2 digits summed up, these 2 digits summed up, these 2 digits summed up, etc., etc. That's gonna be interesting. Huh, okay. What does that mean, though? Vistimefeld spring theory might be helpful here. Okay, so again, these 2 must sum up to the exact same sum as these 2. These 2 must sum up to the exact same sum as these 2. So again, we have Vistimefeld's ring theory. Let's see, there. We know these 2 together equals the same as these 2 together. And these 2 together must equal the same sum as these 2, these 2, these 2, these 2, and these 2. Okay, so let's break down Vistimefeld's ring theory even more. So, okay, these 2 sum up to the same as these 2. These 2 sum up to the same... Okay, so let's mark these as... Okay, let's mark these as medium and dark. So these 2 sum up to the same sum as these 2. These 2 must sum up to the same sum as these 2, which is also the same sum as these 2. These 2. These 2. And these 2, because of the way the magic square works, right? We know these are definitely, because of the 7 by 7 magic square, this is the same sum as this diagonal, which is the same sum as this row, which is the same sum as this column, which is the same sum as this column and this row. That's why these are all have to add up to the same sum. What does that tell us? I'm not really sure. I still don't really know. But you also have the same sum here, right? So these two equals the same sum as these two, which is equal to the same sum as these, which is equal to the same sum. Oh, that's interesting. So say this sum from the 7 to the 9, I don't know, is n, right? From the 5 to the 7, say that's, okay, so say this is n difference for the sum of the blues, right? We have n difference. We have for the grays, that's going to be the difference between 5 and 7, so that's going to be S. And for the difference from the 5 to the 3 to the 5, let's say that's difference of 5 summed up is the sum. So F plus S plus N equals 30, guaranteed. Does that tell us anything? I don't know. We know the sum of all of these is equal to the sum of the Fistmefel corners, right? So the Fistmefel ring is equal to the sum of the 2 by 2 corners in a 9 by 9 grid. And that's equal to 3 times n, because again, is it 3 times n? The difference between this is n. Maybe it's 6 times n. We have 1 pair, 2, 3. So 1, 2, 3, 4, 5, and 6. Right, so 6n plus 1 and 2, 2s. Okay, so we have the formula 6n plus 2s. I don't know if this is getting us anywhere, plus 2s equals, we have 5 f, 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 f. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. 8f. Whoops. So we have 6n plus 2s equals 8f. How do we solve this formula? I don't know. Obviously 10 works. If every single one is 10, that works. But can we have any other combinations? That's the question, right? The answer to that might be no, which would simplify things a lot. But I don't know if it's an assumption I don't think we can make that assumption. We have to sort of prove this, right? But we are guaranteed this, right? We know this formula has to basically be inequality because we've proven this, right? We've shown Fistmefel's ring theory works. We've shown what these add up to, right? This is obviously adding up to f. This also does because of the magic square. So f and f, f and f, f and f, f and f, f and f. We do know these form essentially 5 interesting. A row of this is, well, okay, let's show these two rows. So this row plus this row is equal to 2 times the sum of the 5 by 5 magic square, right? Because they're guaranteed to be the same sum. And if you add up what these are, this has to be the difference between 3 and 5, the 3 by 3 magic square and the 5 by 5. Same with these two, same with these two, same with these two, and same with those two. So that must be 5f times 2. Is that right? No, 5f. So the f is the difference between the 3 by 3 magic square sum and the 5 by 5 magic square. Okay, 3 by 3 magic square sum is 15. And so f is the difference between the 5 by 5 magic square sum and 15. So 5f equals 2. Right. So we have 5f, because again, this is 1, that's 2, 3, 4, and 5. So that's 5 times the difference between, so f equals, again, the difference between the 5 by 5 sum and 15. Five f equals 2 times f plus 15. Is that right? Right, because f is the difference between, maybe I should just make, it makes this, okay, so setting essentially the difference between these is easier for this formula, but it's not as easy for this formula. Okay, so 5f, we know this is 15 plus f. So that would mean this is 30 here, right? Because 15 plus f times 2 is 30 plus 2f. Okay, so that would mean that on this side of the formula, we have 30 plus 2f. So 5 times f equals 15, which is the 3 by 3 sum, plus f, all multiplied by 2, right? Because there's 2 sets of them, 1 here and 1 here. So those are essentially equal. Therefore, we have 5f equals 30 plus 2f. Therefore, we know 3f equals 30, which means f has to be 10. So we've proven then the difference between the 3 by 3 and the 5 by 5 magic square is 10. And I think we can show that also for the rest, right? So this is 1, 2, 3, 4, 5, 6, and 7. So we know f is essentially 10. So 7s, actually it's 7, yeah, 7s, because again, this adds up to s, this adds up to s, same here, same here, same here, same here, and same here. So that's 7 s's. Equals, we know this is 25 here, so this is 25 here. Ooh. That's, thinking about it, that's not good. No. Okay, because, yeah. Because it's a magic square. So again, the sum of this is essentially whatever this is plus s, right? So this magic, and we know the magic square value, the magic sum value for the 5x5 is 25 guaranteed. So 25 is guaranteed there, plus s times 2 again equals this. So again, 7s equals 50 plus, which is 25, plus s, time all of that times 2. So that would be 50 plus 2s. So therefore, we are guaranteed 7s equals 50 plus 2s, which means 5s equals 50. So s, the difference between the 5x5 sum and the 7x7 sum, is also guaranteed to be 10. And that's just because of the properties of the magic square. That's actually very cool. So that we have proven then that the difference between the 3x3 magic square and the 5x5 magic square is 10. And the, what do you call it? The 6 by from the difference between 5x5 and the 7x7 magic square is also 10 because of just the way that magic squares work. The way the magic squares work and the geometry of these magic squares, because they're like Matryoshka dolls and they're essentially embedded one within the other. We know that these outer ones, again, these two must sum up to the same sum as these two, which is the same sum as these two, which is the same sum as these two, which is the same sum as these two. Because of that, therefore, we know this is 5f, and that 5f is equal to the same sum as any row or column is in this 5x5 magic square. And since this row is essentially 15 plus f here, we know it's guaranteed to be 15 plus f is equal to 2 times 15f, because these are two rows in that 5x5 magic square. They have to equal the same as 5f, and therefore we have that formula. Same with the 7x7. I wonder actually if it instead of Matryoshka dolls, it basically kept growing like in one direction. So say this 3x3 here expanded just below and to the right. I think it might be the same, just because they're magic squares. I think this is an inherent property of the magic squares, and having it increase essentially proportionally in at least two directions makes it that way. But I don't know that. I think it does, actually. So say this 3x3 essentially went this way. Is it? No, I think it actually is because it's embedded in each other. That you have this property. That these essentially must add up. So since these two must add up to 10, right? Say this expanded this way, right? Say it expanded this way. This is just actually some theoretical stuff. You know these two add up to 10, but you don't have any information about, well, you have these two, these two, but you don't have a guarantee between these two. So you don't really have a formula here that you can create where you have one side equals the other side. Whereas in the Matryoshka versions of the magic squares, you do, right? Because you can have these two, we know, these two we know, these two we know, these two we know, and these two we know. And we know the full amount for these. So each of these are 10. So f is 10, s is 10, and n is 10. So we are guaranteed that because of the Matryoshka part of the magic squares. Because of that, that's interesting. We know this and its opposite must add up to 10. Therefore, if this is 5, that would guarantee this is a 5 here. But again, we can't have repeats in any row or column. So this cannot work as a 5. These two cannot work as 5s because this 5 will guarantee that's a 5, and this 5 will guarantee that's a 5, and this 5 will guarantee that's a 5 to add up to the magic number for the 5 by 5. So none of these can be 5. Where is the 5 in this region? It must be here. So this is 5, which guarantees this is 5 here. We know in this column, there has to be a 5 somewhere because we don't have a 5 because this is a 5 in this region. So either this is 5 or this is 5. That means correspondingly, this has to be 5 or this is 5 because we know these add up to 10 also, and these corners add up to 10 also. We just don't know which one. Okay. Oh. So I think the fives can never be on the same row or column. They have to be on the diagonals, right? Because if they're not, they would guarantee add up with another 5 in the same row or column. So this, I think this has to be, one of these is 5, and one of these is 5, and one of these is 5, and one of these is 5. Well, this can't be 5 because of the 5 in the region. That means this cannot add up to 5 with that cell. So this must be a 5 and a 5 here to add up to 10. Because again, 5 cannot show anywhere else in the magic square, because if it were, it would add up with the same column or the same row to add up to 10. So this is 5, which means this can't be 5 here, which means this can't be corresponding 5 also. So this is guaranteed to be 5, and that's guaranteed to be 5. Interesting. Interesting. So we should have all the 5s? No, we don't. We have 1, 2, 3, 4, 5, 6, 7. Okay. So we're missing a 5 from this region. 5 cannot be here. 5 cannot... Ooh. Okay, so that logic was not correct. Interesting. We have some problems here. Every difference does... We are guaranteed to have it be 10. That means 5 has to be on the diagonals, period, right? But the problem is we don't have 5 on this 3 by 3 diagonal, and that's the issue, right? Hold up. Let me... Are we guaranteed... I think in a... Let me look this up. I don't believe we have to have the digits 1 through 9 in a magic square. Is that correct? Let me look at the post. I'll be right back. Okay, I'm back. This is not guaranteed, in fact. I think yeah. A magic square is specifically, you do not have to have unique digits. You just have to have the rows and the sums add up to the same value. And if that's the case, Right, you could have odd digits here. So this is not guaranteed to be... Huh. So we actually don't know if this is 15, really. I'm pretty sure it's going to be. But we don't know. Okay. From expanding from... This has to be a 5? Okay, so maybe we don't even know if there's a 5 here. We do know... We don't know, actually. Okay, so my assumption in the first place was wrong. This 3x3 magic square, we don't know if it adds up to 15 for every row. Let's try to prove that. Let's try to prove that. So this is not necessarily 5 in the middle. We don't know what that is. Okay, so let's try to prove every cell, every row, and every diagonal of the magic square adds up to 15. How do we go about it? So we have it for if this is 15, every other one must be 10 to add up to it, right? But we are not guaranteed it anywhere else. So let's just refresh. Okay. So the sum of these two. So for the going from 1 to 3, we're going to mark that as t. So that's one t, that's another t, this is another t, this is another t. What we have here is 3t. So say this is t. This is 1t, 2t, 3t. Equals the same as this digit. So we'll say O. So we have 3t equals O plus t times 2. So 2O plus 2t. Therefore, t equals 2O. Okay. Interesting. So t equals 2O. That means this is guaranteed 1 through 5. If it's 1, that doesn't work. Right? If 1 is here, you have 2 t's, but there are 2 t's have to be in the same row. And 2 t's to add up to 2 would be 1 and 1. And therefore, we have a contradiction there. So O can never be 1. What happens if O is... We can have O be 2 through 5. So say this were 2. That would mean this is guaranteed to be 1, 3, and 1, 3. That would mean this is 1, 3, 1, 3 to add up to 4. And this would have to be 1, 3, and 1, 3 to add up to 4. I guess it could be 1, 2, 3. So this is potentially possible. Okay, that's potentially possible. Interesting. So right now, this is possible. The question is, what happens if after we expand it? So again, we have the 3 to the 5. So we have 5f equals 2 times 6. So that would be 12. Plus 2 times f. Right? Because f is the difference. It's 12. It's 6 plus f here. So that means 3f equals 12. Ah, and then f would also still be 4. And then we'd have a contradiction, because then this would be 1, 3, and 1, 3. We'd have five cells requiring the digits 1 through 3, which are obviously only 3 cells, and therefore it'd be contradictory, because we'd have to have a repeat. So that's why it can't be 2. And I think each one essentially has to... So if you have 2 here, that forces this to be 6 to add up for every row. 6 times 2 plus 2f equals 5f. Therefore, you have 3f equals 12. F would be the same. So f is always going to be the same as t, which is always going to be the same as s, I believe. So if we try to have 7, so we tried that with 2. What happens if it's 3, right? So say this was 3. T equals 2 times 3, which would be 6. Right? So then 6 plus 3 is 9. And that's the sum of each the 3 by 3 magic square sum. So 9, so you have 5 times f equals 9, the quantity 9 plus f times 2. That would be 18. So again, you have the same thing, right? So then t is equal to essentially f is equal to essentially what t is, and t is essentially 2 times whatever this O is. And because of that, we know that you're going to always continuously expand by that amount, which is 2 times 3. But if you expand 6, so you expand from 3 to 3 plus 6, that's 9, is the sums. 9 plus 6 is 15. So that's 3 to the 3 by 3, which is sum of 9. You add again another 6. 9 plus 6 is 15. That's for the 7 by 7. And then you add another 6 for the 9 by 9. That means the sum of any row is 21, which is not the correct sum. It's 45 guaranteed just because of irregular Sudoku rules, because you have to have the digits 1 through 9 once each in every row, column, and, well, not diagonal, every row and column and region. But the rows and the columns must add up to 45. So because of that, if f is always going to be equal to t, which is always going to be equal to s, which is always going to be equal to n. So essentially, to add up to 45, from this we know n equals s, which equals t, which equals f, which equals t, which equals 2 times O. So because of this, the sum of a row is obviously O plus T plus F plus S plus N. And since these are all 2O, O has to equal, this must be, the sum of a row is 9O, 9 times O. 9 times O must equal 45, and because of that formula, we have O equals 45 divided by 9, which is 5. So we've proven that this central box has, the central O, which is one cell, has to be a 5. And because of that, but the thing is, we are not guaranteed, in fact, since O is 5, we are proving that T, F, N, and S all must be 10. So 5 can never be anywhere except along the diagonals. And we had that intuition eventually, but we didn't apply it to the 3 by 3 magic square because we were assuming that the 3 by 3 magic square had to be So actually, we don't actually have Fistmafil's ring. Because this is not guaranteed to be the digits 1 through 9. We don't have Fistmafil's ring theory. That is not correct. Because for the magic square, it's only the sum. It doesn't have to be the digits 1 through 9 guaranteed. So we don't have Fistmafil's ring theory. That is not going to work for us. Because this is not the digits 1 through 9. It has to actually, in fact, be 5 multiple times. Because 5 can only be on diagonals. 5 can never be on non-diagonals, because if this is a 5, its corresponding digit to add up to 10 has to be in the same column or the same row. So that means 5 is guaranteed to be on the diagonals. Well, we know this is a 5 here. Where can the 5 be on the diagonals? 5 cannot be here. So let's clear things up. This is guaranteed to be 5. 5 is going to be either here and here or here and here. We know in this region here, where is the 5? Cannot be here. Cannot be on any non-diagonals, so it must be 5 here, which forces this to be 5 to add up to 10. Because we know going from 3 by 3 sums to 5 by 5 sums is 10, is a difference of 10. So this must be 5 here, which makes this 5 here. This 5 eliminates 5 in this corner. Well, that means this can't be 5 to add up to 10 here. So where are the 5s along this diagonal? Along this 3 by 3, it must be here and here. And therefore we've shown where the 5s have to be here. Where are the 5s in this 7 by 7? We need a 5 in each one. In every 1 by 1, every 3 by 3. We need 2 5s in every 3 by 3. We need 2 5s in every 5 by 5. We need 2 5s in every 7 by 7 because they cannot be along the non-diagonals. So 5 cannot be here, so this can't be 5 here, which means this must be 5 and 5 here. That eliminates 5 in these corners here. So where's the 5 in the rest of the diagonals? It has to be here and here. Okay. That's interesting. So apologies for, well, actually, I doubt it was just a bad assumption. I wasn't used to it, but good thing we checked it, right? We double checked it and we figured out, well, actually, we were stuck if we couldn't. So this has to be essentially the 5 by 5 correctly here. So we have all the 5s set. Now we need to figure out where things can be. We know these two digits must be some combination of digits here. This can never add up to 10, because anything in a 1 by 2 ratio is going to be 3 times something. But that doesn't really help us much, because we just know this 3 by 3, these add up to 10. There's nothing here that means this has to add up to 10. We know every pair in the same magic square must add up to 10. This must add up to 20. This is very interesting, actually, because then you have, these are essentially similar to like XV coordinate things, right? Where do we start coloring, though? Hmm. These two. These two add up to 10, these two add up to 10, these two add up to 10, but we don't have any information there. So do these two add up to 10. This adds up to 30, this is 20, this is... Oh, this adds up to 10. And this adds up to 10, and this adds up to 10. Okay. We're going to make this orange and this blue. Actually, they have to be the same. Huh. This adds up to 10 with this, and this digit adds up to 10 with this. So these must be the same digits. That means, and these two add up to 10, so that means this is the same digit. That means all of these must be the same digit. Huh. Interesting. Right, because of the way that the 5s work, we know these add up to 10. These add up to 10, this adds up to 10, and this adds up to 10. Well, yellow and orange can no longer be here, here. They can no longer be any of these cells. Because we have all of them for those rows and those columns. Where is orange and yellow? Oof. Where's orange in this region here? Again, we have all the oranges here. It cannot be here. Obviously, that's yellow. Orange has to be one of these two cells in this region. Because orange has to be one of those two cells, it must add up with the yellow to add up to 10. So yellow is correspondingly here. Okay, do we have any other ones? Orange cannot be here. Yellow cannot be here. Yellow has to be one of these 4 cells in this region. Because it can't be anywhere here, so it's one of these 4. Well, it can't be here because we know yellow here. You can't be here, so one of these 2 is guaranteed to be a yellow. Okay, let's not do this one then. Okay, so we're guaranteed an orange here, which means yellow has to be one of those 2, but it doesn't have to be this one necessarily. Where's yellow in this region? Yellow cannot be here, here, or here. So yellow has to be one of these 3. That doesn't tell us much. Okay. Orange cannot be here. Orange cannot be here. Orange has to be one of these 3 cells. Okay. Orange in this region cannot be here, here, or here, so it must be one of these 3 cells. So orange is here in this 3 cells. Orange is here in these 3 cells. Where's orange in column 8? Can't be here because of one of these must be an orange. Can't be here. So it can't be here because of this orange can't be here. So orange is one of those 2 cells there. This, I guess yellow would be here. Interesting. Okay. Where is orange in... Okay, we know orange in this region. We don't know where orange is in this region. Cannot be here. It cannot be here. It's one of these 6. Or I guess one of these 5, technically. That's too broad. Anyways, orange in this region cannot be either of these 2. So it's one of these 6. Ugh, that's pretty broad. We know there's a guaranteed yellow here. There must be a corresponding orange here. So since yellow's here, we have a definite corresponding orange here. That eliminates orange in the rest of the column. Aha! So that means in this region here, where's the orange? It must be one of these 2 cells. So it cannot be orange here. We know orange has to be one of these two. That means there's a guaranteed yellow in one of those two. Well, that doesn't tell us very much. Hmm. Okay. Huh. Ah, we know there's a guaranteed yellow here to match this guaranteed orange here. Because these must add up to 10. And orange is definitely one of these two, so yellow must definitely be one of these two. That means this can never be yellow. So since this can never be yellow here, this can never be orange. So that can't be orange. So we're guaranteed an orange here or here. That would guarantee... Oh. Okay. If this is orange, this would be correspondingly yellow. If this is orange, this would be correspondingly yellow. But that doesn't tell us much. Oh, this can never be orange because of this is orange. So this can't be orange. Therefore, we are guaranteed this is an orange here. Because again, this can't be orange because that can't be yellow. And then remember, these two must add up to 10. So since this is orange, this is guaranteed this is a yellow, which means this cannot be yellow. So yellow has to be here, which means correspondingly, this must be orange. So this can no longer be orange. This can no longer be orange. So orange has to be in a 1 to 2 ratio here. It's in a 1 to 2 ratio here. But we don't know which one it is. So yellow corresponds to this orange. Yellow is also corresponding to this orange. We don't know which. In this region, orange is one of these three, which means yellow would have to correspond to one of those three. Oops, not blue. But we don't have any information there. We are guaranteed orange one of those two. Oh, yellow. Does yellow? No, yellow does not have to be there. So if this is orange, that means yellow's there. If this is orange, that means yellow is there. But we don't have any guarantee. Huh. Orange has to be one of these two cells, right? Cannot be, this orange cannot be here. And we know it can't be here because of one of these two having to be orange. So orange had to be here. So that's why this couldn't be orange. So orange was one of these two. Since orange is one of these two, that must have a corresponding yellow to add up to 10 here. So this is guaranteed to be yellow, which means yellow cannot be in the rest of that region. Therefore, where is the yellow corresponding to one of these three cells? Again, yellow can't be here, so orange cannot be here. Therefore, in this region, orange can't be here because of this orange. Orange can't be here because of this orange, and can't be here again because of this orange. So orange must be here, which forces yellow to be here, so this can't be yellow. This orange eliminates orange here, so this is orange, which means that must be a corresponding yellow. And then one of these is orange, one of these is yellow. This yellow means this can't be yellow, though. So this orange means this can't be orange. So we know where the oranges and yellows are, right? This orange means this can't be orange. So this is orange. This is yellow, correspondingly to add up to 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 yellows and 9 oranges. Interesting. Hmm. Um. Hmm. What other regions do we do? Um. Okay. Let's do these, I guess. We're going to make this blue and red correspond to each other, and this is pink and green are going to correspond to each other to add up to 10. So this must be blue or pink here, a combination. That means this must... Okay, so red is here. Um... Hmm. Huh. Huh. I don't know if this tells us much information. The yellow and orange was very helpful. We are guaranteed that these have to be adding up to 10. But we don't have as much information here. Hmm. Maybe we start coloring these? I don't know. We do know that... Hmm. This corresponds to something like here. And then this would correspond to something like here. These two must correspond together. So let's make that red and blue. That means the rest of this has to be green, red, and dark, right? Okay. So these three are green, red, and dark. What do they correspond to? This cell must be here. So this is blue, pink, or medium. This is corresponding to that, blue, pink, or medium. Same here, blue, pink, or medium. Does that tell us much? Not particularly. We know this adds up to 10, and this adds up to 10. But we don't know guarantee that these must be sets of the same set. We know this adds up to 10. Hmm. What does that mean here? Don't think that really helps us much. Hmm. Hmm. Yeah, that's not helpful. Oh, this can never be all sets of 10, right? Because we know none of these add up to 10 with each other. This adds up to 10 with that. This adds up to 10 with that. This adds up to 10 with that. And these three must be different cells. That's not true. It could be red. You could have blue-red here. Ooh. Oh! No. Hmm. Hmm. Never mind. Hmm. So what are the possible colors here? Green, red, dark, and pink and medium. Green, red, dark, pink, medium. Green, red, dark, pink, and medium. Okay. Unfortunately, we don't have any information there. Oh, we know this adds up to 10. Guaranteed. So this has to add up to 10. It cannot be red then. Red would have to force a blue there. So this is not red. We know because we know these two add up to 10. Red could still be here. Hmm. 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 Interesting. Huh. We are guaranteed one of these is red. That means the other two must add up to 10. Well, this can never then be green or dark. Because green and dark doesn't add up with the other green or dark to add up to 10. The green adds up with pink to add up to 10. And the dark adds up with the medium gray to add up to 10. So this can never be green or dark. It could be red, pink, or medium, which means this has to add up to 10 with it. So this is blue, dark, or red. No, not red, green. Blue, dark, or green. That doesn't tell us too much, unfortunately. Oh, can't be dark because of the dark in the region. So this is blue or green, which means this must correspondingly. So blue matches with red. Green matches with pink. So this cannot be medium. So this is red or pink. That means... I mean, this still could be red, which could mean this could be... Oh, no. If this is red, this has to be a green dark pair. Okay, so this is where we're getting it. So if this is red, this would be a green dark pair, but that doesn't add up to 10. And we know blue and red add up to 10. So this can't be red. This has to be pink, which means this corresponds to green here. That means green cannot be here. Green has to add up to 10 with this, and this must be a red-green pair, which eliminates green and pink in the rest of the row. So this must be a medium and dark pair here. Now, what does that tell us? I don't really know. So this is green or red, which forces this to be blue or pink. And this is blue or pink here. Okay. This can't be red because of the red-green pair in the region. So this is dark, which means this must be medium. Since this is medium, this cannot be medium. This is dark, which means this can't be dark. This is medium. Interesting. Okay, so we have medium and dark pairs then. Already set. This is medium, which eliminates medium in the rest of the region. Where is the medium in row 1? It must be one of these 3 cells. Cannot be here because of the medium there. So medium has to be one of these 2. Well, if medium's here, that means this is dark. If medium's here, that means this is dark. So dark has to be one of these 2 cells. We don't know which. Hmm. Interesting. Hmm. So this is guaranteed to be pink. Ah, what are the pair here? These must add up to 10 also, because we have red and blue, which adds up to 10, and pink and green, which adds up to 10 here. So this must be medium and dark, which means this can't be dark. This is medium, which forces this not to be medium. This is dark because of the what the columns have. Again, this is not helpful right now, so let's not match that yet. Okay. Medium in row 5. Oh, this could be medium here. Oof. Where is dark in this region here? We guarantee this is dark and this is dark. So dark cannot be any of these. This is orange. So dark has to be one of these 2. If this is dark, that means this is medium here. And this must be corresponding medium. Okay. That's not too helpful. But we do know dark is one of those 2. Pink has to be one of these 2. Hmm. Okay. We must have pairs adding up to 10 in all of... Okay, so what are the pairs remaining in column 7? Or the colors, I should guess. We have everything... so we have... We don't have pairs, actually. So this must be a pair here. It cannot be green, pink, because of the green in the column. Cannot be dark, medium, because of the dark in the column. So this pair that adds up to 10 must be blue and red. This is a blue-red pair to add up to 10. That leaves the remaining colors as pink or medium. to match the green and the dark here. This is pink or medium. This must be correspondingly green and dark, right? Pink matches with green, medium matches with dark. That means this is a blue-red pair here. Which means we have a blue-red pair then in row 9 and row 1. What are the remaining digits in remaining colors in row 1? They have to be medium, dark, and green. Medium, dark, and green. Medium, dark, and green. That means this is correspondingly... So this is medium, darker green. This is medium, darker green. Medium and dark match with medium and dark. So it could be medium, dark, and pink here. Same with this. This is medium, dark, and pink. And this is medium, dark, and pink. Okay. This is medium, so this can never be medium here. Since this can't be medium, this can't be dark here. This is dark, so this can't be dark. Since this can't be dark here, that means this can't be medium here. Where is the medium then in row 1? It has to be here. So this is medium, because we have a green dark pair in row 1. This medium forces this to be dark. So this is dark here. We have a pink medium pair here. What are the remaining digits in, or remaining colors in this region? We have blue and red and green. That means this is correspondingly blue, red, or pink to add up to 10. Okay. This is blue, red, or green, which means this is correspondingly blue, red, or pink. Right? That's fine. Okay. This is pink or medium, and this is pink or medium, so this must match this cell there. That means this cell must match here. So this is blue, green, or red. That forces this to be blue, red, or pink, correspondingly, to match. The remaining digits actually in this region can't be medium or dark, yellow, or orange, so this must be, what, blue, green, or red, because pink has to be one of these two? Is that right? Can this be pink? Maybe it could be pink. So we have pink here, blue, red, green, pink, which means this is blue, red, green, pink. Okay, that seems fine. This is also blue, red, green, pink. Because of, not orange, blue, red, green, pink. Because of the remaining colors in column 8. That means this is also blue, red, green, pink. And that's correct, too. This cannot be green because of the green dark pair in that region. So since this can't be green, this cannot be correspondingly pink. Where is the pink, then, in column 8? These can't be because this can't because of the pink medium pair in there. This must match this cell because this must match that cell. And it can't be pink here because this can't be green because of the green dark pair in the region. So this must be pink, which means this can't be pink. So since this is pink, that must match here to add up to green. So this is green, which means this can't be green here. This pink also means this can't be pink. So this is a blue-red pair. That meaning this is a blue-red pair to add up to 10. This can't be red because of the red in the region. Since this can't be red, this is blue or pink, which means this can't be blue here because blue would have to have red to add up to 10 with it. So this is red or green, which means one of these two is blue. That doesn't really change much. Okay. Where are medium and dark in column 6? Well, dark could be here. Ooh. Okay. So dark is one of these two. Medium cannot be here. Medium cannot be here. Medium could be here. In fact, these two add up to 10. So either this is blue-red or it's green-pink. That means these two, one of these two must be medium gray to add up to 10 with this. Yeah, because this can never be medium gray because it must have dark there, if that's the case. Therefore, medium gray has to be one of these two cells because there's no other place for it in row 8. Since medium has to be one of these two cells, this can never be medium. So it has to be pink here, which makes this not pink, so this is medium. Therefore, that forces this medium gray has to be somewhere in column 9, can't be here because of the medium in the region. Can't be either of these two, so this must be medium, which means this can't be medium. This is pink, which eliminates pink here as a possibility, so that's blue, which means this can't be blue, that's pink. Blue and red add up to 10, so this must be red, which means this can't be red, that's green. We have, in column 4, a blue-red pair missing, and blue cannot be here because of the blue in the region. So this is red, which makes this blue. That eliminates blue from being here, so this is red. That red eliminates red here, so this is blue, which means this cannot be blue here in that region. Therefore, this can't be red here. Therefore, this matches here, so this can't be red either. This is blue or green. Blue or green matches with red or pink, so this can't be blue here. This red eliminates red here, so this is pink. Pink must be with green to add up to 10. This pink eliminates pink here, so this is blue. That eliminates blue here. So this is a red-pink pair, which means this can't be red. This green has to be green here because it doesn't have any other place in this region. So that green eliminates green here. So this is dark. That can't be dark. This is green. This can't be green. That's blue. Blue matches with pink. Sorry, red to add up to 10. So this is red. This can't be red. This is pink. Okay. Therefore, this blue here eliminates blue here. Well, we already knew that. This is red, which means this can't be red. That's blue. This matches with this cell to add up to 10, so this must be green. This can't be green anymore, so this is dark, dark, and medium add up to 10. Remaining color in this upper left-hand region is green. Green must match with pink to add up to 10. This can't be green, so this is red, which matches with the blue to add up to 10. Remaining digit in remaining color in row 2 is dark. Um, remaining pair here is medium and dark in row 6. And this can't be dark, so this is medium, this is dark. Remaining pair in row 5 are blue and red. And so far, they seem to be either possible. This cell is medium. So that's a put 10 with that cell. Okay. Orange has to be 2 or 4. Because it's in a 1-to-2 ratio with 2 other colors. Oh, this is a blue here, which means this can't be blue here. That's red, which forces this not to be red, so that's blue, which means this can't be blue, so it's not red, which means this is a blue. Okay. Or red is in a 1-to-2 ratio with medium. Blue is also in a 1-to-2 ratio. But it's in, this is, orange is 2 or 4. So this must be 1, 2, 4, 8 here. So orange is 2 or 4. This is 1, 2, 4, 8. This is 1, 2, 4, 8. Red is, it adds up to 10 with blue. So that means this is 2, 6, 8, or 9. But we know 2 and 4 have to be in the blue, orange, or green set, right? Either this is, orange is 2, and it's in a 1-to-2 ratio with 1 and 4, or it's 4, which is in a 1-to-2 ratio with 2 and 8. So this can never be 2 or 8. Therefore, red must be the 6s. So since reds are the 6s, blues must be 4, which means oranges must be 2 and greens must be 1. Well, greens add up with the pinks to add up to 9. And mediums must be 3 to be in a 1-to-2 ratio with 6. That means yellow corresponds to orange, so yellows are the 8s, and the darks must be 7s. And that's the solution. Pretty interesting. Lots of things that you have to derive, which makes it hard. But it never was really that hard. I always sort of felt like I knew where I had to go with this, right? And the irregular shape definitely forced some constraints on where these colors could be. So that was very helpful. Still, definitely a hard puzzle, but very interesting how it all came together. Also interesting that I completely messed up the magic square, but eventually came to the correct conclusions with it, with the 5s, right? That was very cool, actually, just because of the way that the Matryoshka magic squares worked. I don't think it works if it just expands any other way. But because of the way that it was nested within each other, all the magic squares were nested within each other, that forced these to be sums of 10 to increase continuously, right? Pretty cool, pretty cool. Anyways, I hope you enjoyed this solve, and I'll see you next time on Frank Puzzles. Take care.